wings like a bird of doom as it ships.
Okay, section 1.3, we're going to continue on with limits, and we're going to look at one-sided limits. So we'll get to that in just a second. First thing we have to do is we're going to talk about piecewise functions, because for everything we do today, we're going to use piecewise function. So what is a piecewise function? It is defined by multiple subfunctions, each applying to a certain interval of the main function's domain. It's one of these things that sounds really complicated. It's not quite as complicated as it sounds. So, for example, here is a piecewise function. All of this right here is a piecewise function. So we have one function that's called f of x, but then f of x has two subfunctions. It has x squared and also 2 minus x. And whether you use the x squared or the 2 minus x depends on which part of the domain you're using. If you're using any x value that's less than or equal to 1, you plug it into x squared. If you use any value that's more than 1, you plug it into 2 minus x. So let's start by graphing this here. Let's see, why don't we start with the x squared, I guess. You know what x squared is. Don't graph this for a second because I'm going to erase a whole bunch of it. But x squared is a parabola. It's the mother function parabola that has a vertex at 0, 0. You go over 1, up 1, over 1, up 3, 1, 2, 3, over 1, up. Well, wait a minute. I don't even need to do this side, do I? Because we're only interested in all the x values that are less than or equal to 1. So I like this point. I like this point. But this point up here, it's outside this domain that we're interested in. So I'm going to go the other way. Over 1 and up 1. Remember the step pattern, right? Over 1 and up 3, 1, 2, 3, and over 1 and up 5, 1, 2, 3, 4, 5. So this part of the piecewise function looks something like this. This is very hard to draw. Yeah, pretty good. It continues up this way, but it doesn't continue here. It just stops because it only goes up to the point where x is equal to 1. As long as x is less than or equal to 1, it follows this. Okay, now we're going to graph this. This is 2 minus x, or another way you might want to write that is y equals negative x plus 2. If you think of it that way, negative x plus 2, it's just a line, isn't it? And we can draw that line. So it would have a y-intercept of 2, 1, 2. Again, I'm going to put this line, I'm going to erase it again so you might know how to put it. And it has a slope of negative 1. So that means down 1 and over 1, and down 1 and over 1, and down 1 and over 1, etc. Now, here's the thing though, remember, we're only drawing all the points that are greater than 1. So this point right here is not part of it. Even this point right here isn't part of it, but we're not going to erase it because that was part of the x squared function. So we're going to keep that there. And all we have to do is draw this line, which I'll probably do a poor job of, but something like that. And we've done it. We've drawn the piecewise function that's listed right here. Now, it's time to introduce us to one-sided limits. So basically, there's two types of one-sided limits. There are left-hand limits and there's right-hand limits. So what's the difference? A left-hand limit is the limit of f of x as x approaches a from the left. And what this looks like, if we were to write it, it looks like the limit of f of x as x approaches a from the left, so we put a minus sign to show it's from the left-hand side, is equal to L. Okay, and this is approaching the limit from the left. Not surprisingly, what a right-hand limit is, the limit of f of x as x approaches a from the right. And what does that look like? That looks like the limit of f of x as x approaches a from the right. How do we say the right? Plus sign equals L. So let's go back and look at this one that we just drew. And the point that we're really interested in here is the point where the two subfunctions meet. This point right here, right? Let's take a look at the left-hand limit and the right-hand limit right there. So the function's called f of x. So what we can write is the limit of f of x as x approaches 1 from the left equals, and we're also interested in the limit of f of x as x approaches 1 from the right-hand side. So we put a plus there. So let's start with the negative, starting from the left. So as we approach this yellow dot here from the left, so as I'm sliding along this function here, and I'm getting closer and closer to that yellow dot, which y value are we getting really close to? Well, as you get really close to the yellow dot, you're basically at 1, aren't you? So we would say that the left-hand limit of this function is 1. Okay, now let's look at it from the right-hand side. So as I slide on this function and get closer and closer and really close to that yellow dot, which y value, which output value are we getting really close to? We're getting very close to 1 again. So in both the left-hand limit and the right-hand limit, we're getting very close to 1. So we can say, therefore, that the limit of f of x as x approaches 1, I'm not using a one-sided limit, I'm using a two-sided limit. I'm saying the limit of f of x as x approaches 1 is equal to 1. Why am I saying that? Because it approached 1 from the left and it approached 1 from the right, therefore both sides approaching 1. The limit of this function as x approaches 1 is 1. And that should make sense from the drawing here. Come from the left, approaches 1. Come from the right, approaches 1. Okay, let's do another one. Now, I'm going to draw this one on the same graph, which I know is maybe a little problematic, but just work better for space for me. So this time the function is called g of x, and we have our two subfunctions. Let's start with the bottom one because it's a lot easier to graph. This is negative 2x minus 4. It's slope-intercept form. The y-intercept is negative 4. I might be erasing some points, so I might not want to draw this yet. And the slope is negative 2. So down 2 over 1, down 2 over 1, down 2 over 1. And we have to draw this as long as x is greater than or equal to negative 2. So why don't we actually do one more point, go up 2 over 1, actually one more point, and up 2 over 1. And this is everything that we want to draw here. It includes negative 2, so we have this closed dot here, and then it also has all these points here, and I'll do my best to draw a straight line. Okay, great. Now we're going to do the other part, which is this negative absolute value of x. Now, if you remember what an absolute value graph looks like, the mother function just looks like a v right here, and then the negative makes it flip over the x-axis, so it's going to be an upside down v. But I imagine some of you don't remember that. So why don't we just make a little table of values for this one? I'm going to erase this in a second, but you could put it off to the side if you want. So obviously probably the smallest number we want to use is, the biggest number we want to use is negative 2. Why don't we use negative 2, negative 3, negative 4, and negative 5? That'll be more than enough. So if I put negative 2 in here, I get the absolute value of negative 2, which is positive 2, and then make it negative, I get negative 2. Well, everything else is very similar. The absolute value of negative 3 is 3, and then make it negative 3. The absolute value of negative 4 is 4, make it negative 4. The absolute value of negative 5 is 5, make it negative 5. So here's my points. Okay, let's start with this one here. Negative 5, 5. Negative 5, negative 5, negative 5. So that's right there. Negative 4, negative 4. Negative 3, negative 3. Negative 2, negative 2. Okay, negative 2, good, but what kind of dot should we put there? We should put an open dot. How come? Because this subfunction up here is only when x is less than negative 2. So negative 2.1 works, negative 2.001 works, but negative 2 doesn't work. And of course, this function is just going to continue in the same direction like this. So we get like this straight line down here. Great. We have now drawn our piecewise function, this red one. I'll circle it in red to show you that this is the one we're doing right now. And again, what we're interested in here is the left-hand and the right-hand limits. And where we're interested in them, I mean, you could do them anywhere. For example, if I was interested in the left-hand and right-hand limit when x equals 0. So let's say as x approaches 0 from the left, well, as I slide along this function and get closer and closer to 0, and x value is 0, the y value is getting closer to negative 4. So the left-hand limit is negative 4. As I slide along this function, getting closer and closer to 0 from the right-hand side, again, the y value is getting closer and closer to negative 4. So the right-hand limit is negative 4. So obviously the limit as we're approaching 0 here is negative 4. But that's not really the point we're interested in. The point we're interested in is this one where the piecewise function changes, right? Where you get the different subfunction. So we're interested in the limit of g of x, that's the name of this function, as x approaches negative 2 from the left, and we're interested in the limit of g of x as x approaches negative 2 from the right. So let's see what we get for both of those. So if we slide along this, we're starting from the left of this. If we slide along this function and we get closer and closer and closer to -2, but we don't actually get there, what are we getting very, very close to in terms of our y value? We're getting very, very close. We're not quite getting there, but we can get as close as we want to. We can get as close to -2 for our y value as we want. So the left-hand limit is -2. Now let's slide along from the right-hand side, this g of x, this function, getting closer and closer to -2 from the right-hand side. And what value are we getting really, really close to? Which y value are we getting really, really close to as I slide closer and closer to -2? My y value I'm getting very, very close to is 0. So the right-hand limit is 0. I have a left-hand limit of -2. I have a right-hand limit of 0. So what do you think this means for the limit of g of x as x approaches -2 overall? Like not the one-sided limit, but the two-sided limit, so to speak. What does that mean? From the left hand it equals -2. From the right side it equals 0. What's that mean about the limit overall? It means d n e. D and E, do you know what that is? Does not exist. Okay, I guess maybe since this is the first time we're going to write it, I should write it in here. Does not exist. From now on, I'll always just be writing D and E. It happens a lot that limits don't exist. Okay, so the left-hand limit and the right-hand limit have to equal each other in order for the limit itself to exist. So let's summarize what we've just said here. We have said if the limit of a function as x approaches a from the left-hand side does not equal the limit of the same function as x approaches a from the right-hand side, then the limit of f of x as x approaches a does not exist. So that's one thing we've said. We've also said that if the limit of f of x as x approaches a from the left-hand side does equal the limit of f of x as x approaches a from the right-hand side, and if in both cases what the limit equals is L, then the limit of f of x as x approaches a also equals L. Okay, so this first thing we wrote is exemplified by this. Left-hand limit and right-hand limit don't equal each other, therefore this limit does not exist. And the second one is exemplified by the first example. The left-hand limit equals 1, the right-hand limit equals 1, those are equal to each other, therefore the limit of f of x is also equal to 1. Okay, so that's everything we've done. Okay, here's another piecewise function that we need to graph. This time it has 3 pieces to it, 3 subfunctions. This can happen, you can have 3, 4, 5, whatever. Usually they won't give you more than 4, but it's certainly possible. Alright, let's start with the middle one. F of x equals x. Well, x, that's like y equals x, right? That's just the mother function line. It's just that 45-degree angle line. And we're going from -1 to 1. Alright, so it's going to be like this. What kind of dots should we put? In both cases, since it's less than and less than but not equal to, we should have open dot and open dot. Now those might change later, we'll see. Let's go up here, -x minus 2. This is again in slope-intercept form. So we have a y value of y-intercept of -2, so I'll draw that, but I'm going to erase it in a second. And I have a slope of -1. So I should go down 1 and over 1 and down 1 and over 1. But wait a second, we say here, it says here we're interested in all the x's that are less than or equal to -1. So we should actually move up and over. Up and over, and here's a point, and up and over, here's a point, here's a point, here's a point. So we can immediately get rid of these. We know that the graph is going to go up like this. And the last decision we need to make is, should we be changing this to closed or leaving it open? Well, it says right here is that when x is less than or equal to -1, this applies, this subfunction, so it can be equal to this in that case, so I have to make it solid now. That solid is not because of the second subfunction, it's because of the first subfunction. Okay, the next one, oh drat, it is a parabola, x squared minus 2x, and the reason I say oh drat is because it's not in standard form. So You know what? Why don't we just do some plug and chug, as some people say. Let's just plug in some numbers. The x's we're interested in are the x's which are greater than or equal to 1. So smallest value should be using is 1. If I put 1 in here, I get 1 squared, which is 1, minus 2 times 1 is 2. 1 minus 2 is negative 1. So 1, negative 1. Should I put a solid dot or an open dot? Solid, because it says equal to. So there's my first point. Okay, the next one I'm going to put in there is 2. 2 squared is 4. 2 times 2 is 4. 4 minus 4 is 0. Next one is 3. 3 squared is 9. 2 minus 3 is 6. 9 minus 6 is 3. Now, you might actually recognize this. Over 1 up 1, over 1 up 3. It looks pretty good. It's going to be over 1 up 5, but let's just do it to make sure. If we put 4 in here, you get 4 squared is 16. Minus 2 times 4 is 8. 16 minus 8 is 8. It worked. So this is actually the vertex right there. And that's what it looks like. Okay, now that we've got it all graphed, we can figure out our one-sided limits and whether this limit here exists. So it says determine whether the limit of f of x as x approaches negative 1 exists. So in order to do that, first of all, if you have the drawing, you can just look at it and tell whether it exists or not. I'll explain why in a second. But what we're going to do for now, pretend you didn't draw this, because who wants to graph this all the time? You could figure this out by looking at the left-hand limit and looking at the right-hand limit. So the left-hand limit would look like the limit of f of x as x approaches negative 1 from the left, and then we're going to get the limit of f of x as x approaches negative 1 from the right, and then we'll be able to say the limit of f of x as x approaches negative 1. Okay, let's start from the left. So if you're using the graph, the way you do that is you'd look at negative 1, which is right here, and you say, as we're approaching it from the left, what y value is it getting closer and closer and closer to? It's getting closer and closer and closer to negative 1. Okay, how would we do it algebraically? Well, you'd ask yourself, if I'm approaching negative 1 from the left-hand side, so below negative 1, would I use the top subfunction, the middle one, or the bottom? This is greater than 1, or equal. This is between negative 1 and 1. This is less than negative 1, or equal to. And we're approaching from the left, which means less than. So we would use this function right here, this top one. So let's try it. If we put negative 1 into here, we get negative negative 1, which is positive 1. Take away 2, which is negative 1, just like we wrote right there. Great. So you don't need to have the graph. You can just use algebra. We'll do a couple more examples there. So this time we're doing limit of f of x as x approaches negative 1 from the right. As we approach negative 1 as an x value of negative 1 from the right-hand side, which y value we're getting closer and closer and closer to? We're getting closer and closer to negative 1 again. So we put negative 1 here. Let's do it algebraically to show you don't need the graph. If I'm picking a value that's to the right-hand side of negative 1, no, these are to the left-hand side of negative 1. This is what I would use right here. Really, really close to negative 1, but just a little bit to the right. That'd be this middle subfunction right here. So let's try it. If we put negative 1 in there, well, we get negative 1. It worked. Okay, awesome. So we have the left-hand limit is negative 1. The right-hand limit is negative 1. What's that mean for the limit overall? It's negative 1. Okay, now we're going to do the same thing, but we're going to look at the left-hand limit, right-hand limit, and limit itself of when x approaches positive 1 this time. So we're doing the same function, but this time we want to know when x approaches positive 1 from the left, and when x approaches positive 1 from the right, and then we'll be able to say what the limit is as x approaches 1. Okay, so as we approach as we approach 1, an x value of 1 from the left-hand side, so that's right here. As we get closer and closer to 1 as our x value, what's our y value getting closer and closer to? 1 as well. So this equals 1. Let's make sure that worked. Which sub function would we use? Top, middle, or bottom? If we're approaching 1 from the left, that would fall right in here. We're approaching 1 from the left, just a little bit less than 1. So if I put 1 in there, I get 1. So that worked nicely. Okay, now let's approach 1 from the right-hand side. So if I have an x, looking for an x value of 1, but I'm approaching it from the right, I'd be sliding along this part of the function. And as I get closer and closer to an x value of 1, what's my y value getting close to? It's getting close to negative 1. Let's see if that worked. I want a value just a little bit bigger than 1. Well, that would be this bottom function here, bottom subfunction. So I put 1 in there, I get 1 squared, which is 1. 2 times 1 is 2, sorry, and 1 minus 2 is -1. It worked again. So what does this mean for the limit of the function as x approaches 1? Well, the left-hand limit's 1, the right-hand limit's -1. They're not the same, so we get d n e. In fact, I want to skip down to continuous functions right now. We'll come back and do this last example at the end. So we say f is continuous at a if 3 things have to be true. 1, f of a is defined. In other words, a is in the domain of f. 2, the limit of f of x as x approaches a exists. And remember, what that depends on is that the left-hand limit and the right-hand limit are equal to each other. And the last thing is that the limit of f of x as x approaches a has to equal f of a. Okay, so let's go through that by doing this example. Yet another piecewise function. So where's the following function discontinuous? Okay, let's start with the middle one. F of x is equal to 0 when x equals 0. What does that mean? Well, at that one point when x equals 0, the y value is 0. So we just have this 1 point sitting right there. Okay, nice. Next one. Let's do the top. This is a parabola. It has its vertex at 0, 1. But careful, you wouldn't want to put a solid dot there. You're going to put an open dot because it's only when x is less than 0. So open dot, is it facing up or down? Up. And it has the basic step pattern. So over 1, up 1, over 1, up 3, 1, 2, 3, and over 1, up 5. So we have something that looks like this. Goes on forever. But it stops there with an open circle. Okay, let's go down to the third part of the function here, x squared minus 1. This is again a parabola, has its vertex at 0, -1, so that's right here. Should I put open dot or closed? You should put open dot. How come? Because again, it only says greater than, not greater than or equal to. It opens up, because this is positive, and it has the basic step pattern. So over 1, up 1, over 1, up 3, over 1, up 5, over 1, up 7 won't fit, so we're done. So this is our piecewise function right there. So now what we're going to do is we're going to see whether it is a continuous function. Now I'll tell you right now it's not, because I already defined continuous last time as a function that you can draw without lifting your pen. If you're drawing this function, you definitely have to lift your pen in order to do it. You have to lift it a couple times. So it's definitely not continuous. But let's imagine we hadn't drawn the function, because we'd like to be able to do this even without drawing the function. So the first thing we'd want to do is we want to see if it passes criteria 1 here. We want to know, is f of 0 defined? And the answer is, yeah, it is defined. You know right here that f of 0 when x equals 0, y is 0. Or by looking at our graph, if x is 0, if we're interested in x value of 0, which y value would we have? Not this one, because that's an open circle. There's no point there. Not this one, there's an open circle. There's no point there. Right there, that's the point when the input 0. What's the output? What's the y? Also 0. So it passes the first criteria. Second criteria, we need to see whether the limit exists. So we need to see whether the limit of f of x as x approaches 0 from the left, have to see what that equals. We have to see whether the limit of f of x as x approaches 0 from the right exists. And what we're hoping for, it's not going to work in this case, but we would like those two to be equal to each other, because then we'd know the limit itself exists. So let's do this. As we approach 0 from the left, we'd be sliding along here. What y value are we getting very close to? 1. Or if you want, plug it into which one of these subfunctions. Since it's less than 0, it would be the top one. 0 plus 1 is 1. Okay, the right-hand limit as we approach 0. So we're sliding along this function, getting closer and closer to 0 from the right-hand side. Boy, it looks like we're getting very, very close to a y value of -1. Let's convince ourselves of that. If we're just a bit bigger than 0, we're looking at the bottom function down here, the bottom subfunction. So if we put 0 in there, we get 0 squared is 0, take away 1 is -1. So that worked too. Now, what does that mean overall for the limit? The limit of f of x as x approaches 0 is dne. It doesn't exist. So, therefore, f of x is discontinuous at 0. You could tell, again, you didn't need to even do all this. Just if you have the graph, you can just look and see there's a break in the graph. But I'm trying to show you how you could also do it algebraically. As for step 3 here, or criteria 3, what we're saying here is that f of a, or in this case f of 0, has to be equal to the limit. So the only way it would have worked that this was continuous is if we did get a limit here of f of x, and what's more, that limit of f of x would have to be equal to 0, which is the same as what f of 0 equaled. Then we could say it's continuous. Okay, back up to this kind of annoying example. The absolute value, in my opinion, always makes calculus problems more difficult. So I never look forward to seeing it. You might have heard this piecewise notation or piecewise function before. You should have. It was in Pre-Calc 11, one of your least favorite things ever. And what we learned is a way to write absolute value with piecewise notation. Okay, so what we're going to do is we're going to use piecewise notation to rewrite absolute value of x. It's just going to be another way of writing absolute value of x. So I have a question for you. When is it, for which values of x is it, that the absolute value signs would do absolutely nothing? They're just like, they're superfluous, they're unnecessary, redundant maybe. Well, that would be if x is positive, because the absolute value of a positive is positive, or if x is 0, because the absolute value of 0 is still 0. So we can rewrite this. We can just say that absolute value of x is exactly the same as just x if what? If x is greater than 0 or equal to 0. So that's half of our piecewise function. But there's another possibility. What if x is less than 0? Then the absolute value signs actually have to do something. So let's imagine, for example, -2, the absolute value of -2. You know that the answer to that is +2. So what could you think of the absolute value signs doing to that negative to make it positive? You could think of it as making it -2. If you take a negative and make it negative, you get negative, which is positive. So that's why absolute value of x is the same as -x if x is less than 0. Does that make sense? Because if you have a negative x value, when you now make it negative x, it becomes positive x, and that's exactly what absolute value signs do, is they make things positive. So this is the way, and you should get familiar with this is the way that you write an absolute value function in piecewise notation. So what we're going to do is we're going to see what the limits of this are. We're going to see what the left-hand limit is. So the limit as x approaches 0, since that's the key number here from the left of absolute value of x, and the limit of absolute value of x as x approaches 0 from the right. We're going to see what that equals to. Okay. Now you don't need to, but we could sketch this. You know what an absolute value graph looks like. We already talked about it today. It looks like that V has its vertex right at the origin, and it looks like this, right? So as we approach the 0 from the left, so we're sliding along here, we're getting closer and closer and closer to 0. What number are we getting very close to for our y value? 0. Or if you don't want to use the graph, look here. We're looking at when it's less than 0. Would that be the top or the bottom part? That'd be the bottom part. And if we put 0 in here, you get -0, which is just 0. Okay, right-hand limit. So we're sliding along here, getting closer and closer to an x value of 0. Which y value are we getting close to? 0. Or if you want to use here, we're talking about just a little bit bigger than 0. That'd be the top here. And if you put 0 in there, you get 0. Okay, great. So we have a left-hand limit of 0, we have a right-hand limit of 0, so that means the limit of the absolute value of x as x approaches 0 is equal to 0. Since these are equal to each other, that means the limit's equal to 0. The key part of this question, really, I'm hoping this last part, you're like, why are we doing this? This is so much easier than the other ones we've done. This is the key thing I want you to realize. You will have this popping up in this course from time to time. Not a lot, but when it does, these absolute value signs, you need to be able to write it in piecewise notation like this. Okay, we've made it. Have a good one.
His shadow is cast wherever he stands. Stacks of green paper in his red right hand.